Today we are investigating how to predict acid strength by looking at the stability of conjugate bases. As a reminder, base stability describes how reactive a species is to accepting a proton. A more stable base is less reactive, while a less stable base is more reactive. Stronger acids create stable bases. The more stable a base, the less receptive it is to a proton and the stronger the acid counterpart.
There are 5 qualitative predictors that can describe base stability, each with varying degrees of significance. We can remember them with the acronym SERHI.
I remember SERHI by thinking of Sergei Prokofiev.
The letters are ordered according to their importance in determining the stability of the conjugate bases.
In SERHI, S stands for size, E stands for electronegativity, R stands for resonance, H stands for hybridization, and I stands for the inductive effect.
Size is the most significant predictor of base stability, since a larger atom can distribute the negative charge over a greater amount of space, stabilizing the negative charge so that it doesn't need a proton to neutralize it. Therefore, if a bigger atom is connected to the hydrogen, it means it's more stable and therefore the acid would be stronger.
Electronegativity is the next predictor of base stability. A more electronegative atom will increase base stability because it is better able to handle the negative charge. The more electronegative an atom is, the more stable the conjugate base.
Resonance is next. If the conjugate base has more resonance structures, then it can better share the negative charge, making the base more stable and less reactive. More resonance means that the molecule is a more stable base, meaning that its conjugate acid is stronger.
Hybridization looks at the hybridization of the atom that the H+ proton would attach to. If an atom has more S character, then it will be less reactive. When comparing sp3, sp2, and sp hybridization, sp will be more stable since it contains more S character, which is lower in energy than p.
Last is the inductive effect. The inductive effect describes the impact of an electronegative atom on the stability of the conjugate base. This is different than the E, the electronegativity, in SERHI, because instead of looking at the atom attached to the proton, we are looking at atoms further away from the leaving hydrogen. The more electronegative an atom, the greater pull it is going to have on the electrons within the bonds attached to it. This effect cascades through all of the bonds in the molecule, stabilizing the negative charge on the deprotonated atom by pulling it closer to the electronegative atom.
To summarize, when we want to predict relative acid strength, we look at their conjugate bases and compare the relative base stabilities. We can use SERHI to predict base stability.